Thank you for the introduction, and thank you to the organizers for the invitation to give this series of talks at this conference. Very happy to be here. So, as mentioned, the title of the series is Exact Infinity Categories. Exact infinity categories were introduced by Clark Barwick around 2015. And as the name suggests, there are certain categorical structures that are analogous to Quillen's exact categories in the theory of ordinary categories, but that are formulated within the context of the richer infinity categories. So the purpose of this series will be to briefly motivate the introduction of these categorical structures and just to present some general results about them with the idea that this could serve as an invitation both to the theory of infinity categories and to the theory of exact infinity categories in particular. Yeah, I also should say that most of this material I will present is in no way due to me. I will mention this as the talks go along. So I will just somehow present mostly work of other people. So let us begin with some motivation that it is not historically accurate. But I hope it's a motivation that it's acceptable for you. So suppose you're given an abelian category, for example, the category of modules over a ring, and you take an extension closed subcategory. So we know that short exact sequences in A are very nicely behaved, and it would restrict them to E by considering the class of short exact sequences, short exact sequence in A with terms in E. This also inherits these very nice properties. And in fact, well, this comes down by itself, right? Or am I, yeah, is that right? Or am I just imagining this? Let's see, maybe I need to do it like Hagenhoff or maybe hold it, or we'll see. Okay, this is going to be fun. So in the early 1970s, Quillen provided an axiomatization of the properties of the pair E, S. So the underlying additive extension closed subcategory of A together with this class of short exact sequences giving rise to what we call exact categories. So I'm assuming that all of you have preferred examples of abelian categories and extension closed subcategories, and I have seen or worked in one way or another with the notion of an exact category. So I will not give you the axioms right now, but I'll rather remind you that this prototypical example, modulo set theoretic issues, is essentially the only kind of example that exists due to the Gabriel-Quillen embedding theorem. Which says that I have a small exact category, then there exists a fully faithful functor to an abelian category whose essential image is extension closed in A, and such as this functor is exact since admissible short exact sequences, the ones that lie here in S, to exact sequences in A, but also reflects exact sequences. So it detects whether a sequence is in S by asking whether the sequence is exact in A. So preserves and reflects exactness. Okay. Now, we also know that, again, set theoretic issues aside, if I have an exact category, then it embeds, for example, it is bounded derived category, and that this is a triangulated category. And that the image of E in its bounded derived category is also extension closed now in the sense of triangulated categories. So this motivates an extension of this setup to the following situation. So I might abstract this a little bit further. So I might now start instead with an abelian category. So it's a kind of a variant of the setup. And I begin now with a triangulated category. And then with an additive subcategory, which is extension closed. And again, I may consider the following restriction of the triangles in T to E. So this is an exact triangle in T with terms in E. And now the question is, what is the analog of Quillian's axiomatization of the pair E, S in this setting? So an answer to this question was provided by Nakaoka and Palou in 2019. So they axiomatize the properties of the triple now, E, S, and the extension factor in T, so the home into the shift, restricted to the extension closed subcategory E. And the resulting axiomatization is called an triangulated category. Now this series of talks is not about triangulated categories, but let me tell you that if you have not seen this notion before, I also will not give the definition right now, it's a bit technical. But for good reasons, they have become, in the last few years, very popular, for example, in representation theory of finite dimensional algebras. And that's because one is often very much interested in triangulated categories such as the bounded derived category of finite dimensional modules over a finite dimensional algebra and various kinds of extension closed subcategories. Yeah? For example, intervals in KB-Proj or aisles of T structures and various sorts of extension closed subcategories. Given that this notion axiomatizes the good behavior of triangles restricted to those subcategories, it's perhaps not so surprising that this notion is actually very useful to deal abstractly with this setting. Okay. Right. So just now for purely abstract reasons, it is natural to wonder whether there is a variant of the Gabriel-Quillen embedding for X-triangulated categories in the sense of Nakaoka and Palou. Theorem for X-triangulated categories. So in this, maybe towards the very end of this series, we will give an answer due to Jonna Clemens well, we will give, in fact, let's say, a partial answer by passing to the richer setting of, is that how far it goes? Okay. Exact infinity categories. So in this setting, we will give a full answer of exact infinity categories, but this answer is partial because it does not cover the case of X-triangulated categories that are not related to exact infinity categories. So in fact, I do not know, maybe the experts can correct me, but I don't think there is a general version of the Gabriel-Quillen embedding theorem for an arbitrary abstract X-triangulated category. So there are only versions known when we admit a refinement of the notion to a more sophisticated notion like exact infinity categories or exact DG categories in the sense of Xiaofa Chen that were recently introduced in his PhD thesis. So again, let's say that our motivation is to try to understand extension-closed subcategories of triangulated categories. And I'll ask you to, I mean, I assume that, most of you have worked with at least specific instances of this context, so you accept that this is a reasonable context to investigate, and that answering things like the existence of a Gabriel-Quillen embedding can be advantageous both from a practical perspective, but also from a, from a conceptual perspective. Okay? Okay. Now, so that's our motivation, to give an answer to this question, to construct a Gabriel-Quillen embedding for suitable class of X-triangulated categories. Now, as I mentioned now a couple of times, we're interested then in what are called exact infinity categories. So surely to understand that, we first would like to gain some understanding of what infinity categories are. So I will also go ahead and assume that even I know some of you personally, and I know some of you are familiar with the notion of infinity category, and some of you are experts on this, I will assume that this is not the case for everybody in the audience. I will assume this is a nice laughter, that you agree with this, that you're happy about this, you're somehow happy about this. Okay. So I hope that the strategy I will pursue is not disappointing to you. So I will give you no definitions, but rather try to communicate some intuition. There is no time for definitions at the moment in this context. So we will do something else. Yeah, so we will spend the day, well, not the day, I mean the lecture discussing about infinity categories only. So exact infinity categories will only appear in the third lecture. Okay, so first some motivation. So if I have an ordinary category, say a 1 category, for emphasis, I have for every pair of objects a set of morphisms. And the associativity and unitarity constraints in C essentially translate to the fact that these sets are functorial in C. This is a very useful thing because using these home functors, we can formulate universal properties. For example, if I have a commutative square in C, and I have a pullback of this cospan, then I have, for example, for every W, the functorial bijection to the pullback of the corresponding sets of morphisms, right? So I should interpret this side as squares, such as this one, that are compatible with the morphisms in this part of the square. And this, of course, just maps to the pullback, right? And the fact that this map is bijective tells me that for every such a square, there exists exactly one map to the pullback, making the reasonable triangles commute, right? So this is a bijection of sets, of course, right? So in other words, our formulation of universal properties is very closely related to the study of functions between sets and whether these functions are bijective or not. Now, as you most probably have heard, while this notion of category is very useful, and this way to formulate universal properties is very useful, sometimes we face some problems. For example, if R is a ring, I may form, for example, the category of chain complexes of modules over this ring, and then the homotopy category of complexes, so chain complexes of two chain homotopy. And now we know that this is, for example, a triangulated category. Now in this context, for example, if I have a map in the homotopy category of modules, then I can form its cocone, part of a distinguished triangle. And it has almost a universal property. For every morphism A that composes with F to 0, there exists a map A bar such that, I don't know if I call this G A bar is A. However, we make no claim on the uniqueness of this morphism A bar. And indeed, we can see why this fails, because we know triangles give rise to long exact sequences. Okay, this is not going to work if I, well, cocone of F. But here, I still can continue to morphisms to the inverse shift of Y, all of this in the homotopy category, right? And the failure of the injectivity of this map is then closely related to the non-vanishing of this morphism, which is also related, therefore, to the non-vanishing of this abelian group. Okay, so the question is how to solve this problem. So this is the statement is we know that cocone is not functorial. Yeah? So it's not characterized by a universal property, for example, here in the homotopy category of chain complexes.
One question or comment?
Yeah.
Can you not say that a bar, well, it's not a standard universal property, but it's characterized by being unique up to homotopy?
Well, this is of course where we're going to. Yes, we're going to try to understand how we should characterize these objects. Yeah.
But you can also characterize it in K of 1 R, which is not a universal.
Yeah, exactly. We can characterize it as a pair of the non-canonical isomorphism, but this is say unsatisfactory. Yeah. Okay, that's.
I think you may need one middle one.
Huh? This one? Thank you. Okay. So a proposed solution to this problem is to replace sets by richer mathematical objects. For example, in the 1990s, Bondar and Kapranov proposed to use Kelly's theory of DG categories to address this issue. So replace sets by chain complexes of abelian groups or vector spaces or modules over a commutative ring or whatever. Yeah? So here the idea is that instead of asking of some bijections between certain sets, you can formulate statements like, I don't know, the following. So you have some chain complexes of maps between some objects in some abstract category where the maps form chain complexes, or some DG category in formal terms. And you can ask that if you take the chain complex of maps to x to y, and you shift it, so this is the shift of complexes, then there is an object such that there is now maybe perhaps even a quasi-isomorphism of complexes. So there's some kind of abstract shift. So you can formulate universal properties of different kinds. Instead of a set theoretic bijection, you can ask for an isomorphism in certain more sophisticated category. In this case will be maybe some derived category of complexes. And this, in fact, is a very fruitful approach that's used a lot in algebra and algebraic geometry, for example, because a lot of the categories that we're interested in can be replaced by categories with, say, essentially same objects, but where instead of sets of maps or even abelian groups of maps, we tend to now have chain complexes of maps. So this is the DG approach. So this is the idea of replacing one categories by DG, or more generally, so-called A infinity categories. This has advantages and disadvantages. Advantages and disadvantages. So so the advantages are, for example, that we have explicit formulas related that we work with often very explicit chain complexes of maps. And this is adapted. So this context is adapted to algebra and, say, algebraic geometry, or geometry in quotation marks. It's some vague statement, right? Now, the disadvantages of this approach are that, for example, there are very explicit formulas, which makes it sometimes difficult to formulate categorical arguments instead of using, say, diagrams and categorical intuition, but rather we need to translate this into formulas. And then finding what are the correct formulas, it may be complicated. And another disadvantage that is there, for example, is that this is adapted to algebra and algebraic geometry. Yeah? So that means that we, in some sense, cannot capture certain interesting triangulated categories by working only in this context of one category, DG and A infinity categories, right? Now there is another alternative to this, which is to replace sets by some more sophisticated notion called an infinity groupoid. That is meant to be something like a groupoid. So a groupoid is a category in which every morphism is invertible. But now I have invertible morphisms in every dimension possibly. Dimension 1, dimension 2, dimension 3, up to, up to infinity. There is no a priori bound on these morphisms. And well, this is what will lead to the theory of infinity categories in some sense. Now, so again, this has advantages and disadvantages. So among the advantages is that we need less explicit formulas. And therefore we formulate statements in a way that it is more resemblant to the theory of ordinary categories, which can be advantageous. Yeah? So there is no need to translate statements into explicit formulas, but to rather translate them into a correct sequence of application of universal properties, for example. Yeah? And another advantage is that this is very much adapted to the, for example, triangulated categories that appear in topology. And the disadvantages, well, among some of them are less explicit formulas, and that it's adapted to topology. So meaning that sometimes when we're interested in a concrete category that is of interest for us, say in representation theory, by working in this other context, the lack of formulas might make it difficult to compute. So we might want to translate to the other language so we have explicit formulas to compute. And maybe it's a little bit different the way, so it actually, this is maybe an unfair statement because this setting can also include the categories that appear in algebra and topology, although the translation is maybe in some sense non-trivial. Yeah? Okay. So now, next, well, I don't have space there. Okay, so the proposal is to move to this world. Yeah. So this, as I said, the world of DG and A infinity categories is extremely useful. I also like it very much. But for the series of talks, we need to work in this, this world. Yeah, if it will be a series of talks on exact DG categories, then of course we work in DG world. But this is about exact infinity categories, so we need to work in the infinity categorical world. I'm trying to motivate for you why this is reasonable. Yeah. So you might ask yourself, why do we need infinity groupoids? And here really is more the question, actually, or the way I will answer it, is why we need, instead of chain complexes of a billion groups, some more sophisticated structures that are closely related to infinity groupoids called spectra. We will talk about this maybe later in this series. Well, one reason why to move from this language to this language is we have access to refined invariants. So here's an example that I don't know much about. So yeah, if you ask me, I will not know nothing about this. But for example, there is such a thing called Kovanov spectra for knots, links, and tangles, for example. Sarkar, right? This Sarkar, yeah. So I think some of you are interested in such type of invariants, and there are some refinements of Kovanov homology to some more space-like structures that are able to distinguish between links that are not distinguished by just Kovanov homology exclusively. Yeah, but I say I don't know much about this context, but it's just an example of something yeah, some of you might be interested in. Yeah? So we get, from passing to chain complexes to more sophisticated structures, we can get access to, well, more sophisticated structures. Yeah? Or more general structures, maybe I should say. Okay. Yes. When am I supposed to stop? I don't remember when I started.
10:05.
Okay. Okay. Thank you. Okay. Good. Yeah. So today, I hope you have some motivation now to. Okay, it's reasonable to work with infinity categories. So today we will discuss some of the mechanics of infinity category theory. After work of Joyal, Lurie, and several others. And for a while, most results, so basically if I state something without attribution, I mean to imply that it is either due to Jacob Lurie or is somehow part of his very large body of work on infinity category theory. In particular, it's not due to myself, although many things that appear in his book are also originally due to Joyal. Okay, so am I out of Blackboard? I am. So I will then clean. Okay. Only one at a time. Mm-hmm. Yeah, so now the idea is to, instead of telling you what exactly is an infinity groupoid and what exactly is an infinity category, and so on and so forth, I'll rather tell you some of the things that you can do with them. Yeah? Okay, this is now good. Okay. Yeah, and maybe the general message is that thanks to the work of Joyal, Lurie, and several other people, there is, in some sense, fully fledged theory of infinity categories, which is kind of, in some sense, entirely analogous to the theory of ordinary categories. So most of the things that you want that are true in this world are true when interpreted correctly. And most of the constructions that you might be interested in tend to already be available in the literature, which is very convenient. So in a way, the theory has reached a stage which is, in some sense, ripe for use. Yeah? So, by the way, I most definitely do not consider myself an expert in infinity category theory, but I'm more like an enthusiast user of the theory, something like this. Yeah? And I think this is a very good first approach to the theory. Just try to start to use it, yeah? And then sort of get used to it first. Okay. Okay. Put this back here. Okay. So yeah, the first thing. Well. Maybe just tell you in a nutshell, I already tried to indicate what is an infinity groupoid. So an infinity category is like an infinity groupoid. So I have categorical structure with maps in every dimension, 1, 2, 3, 4, and possibly no bound. But without so all of them in dimension 2 and higher are meant to be invertible in some sense. But in dimension 1, they are not supposed to be such. Now, this notion is notoriously tricky to formalize in such a way that one can really work with this. And that's why, for today, I've chosen this approach of rather sketching some of the things one can do with these things. So the first thing is that there is an infinity category of infinity groupoids, just like there is a one category of sets, whose objects are infinity groupoids. Now, one thing that is useful for us to say construct infinity groupoids and also to think about them is something called Grothendieck's homotopy hypothesis, which I will state here in a very vague and very imprecise way. So the first thing is, given a topological space, you can associate an infinity groupoid pi infinity of x called the fundamental infinity groupoid, or the Poincaré infinity groupoid of x. Its points or its objects are just the points in x. The one-dimensional morphisms are the paths in x. The two-dimensional morphisms are homotopies between paths in x. And then three-dimensional homotopies between homotopies, and you go up and up and up and up. Yeah? So in some sense, given topological spaces, we can construct infinity groupoids. But also, every infinity groupoid arises in this way. And I will leave the statement about in which sense arises in an essentially unique way vague. Yeah? But it arises in this way. And in fact, for this reason, infinity groupoids are very often called just spaces or homotopy types of spaces. Okay. So using this intuition from topology, there are many invariants that one can associate to a given infinity groupoid. So if I have an infinity groupoid, I can associate to it a set of path-connected components. Which are somehow the isoclasses in this infinity groupoid viewed as a categorical structure. For every point in this infinity groupoid, I think of it as a kind of space by this translation procedure. In every natural number, I obtain a group, just as in topology, called the kth homotopy group. So it's now a group which is abelian if n is at least 2, just as in topology. Yeah? Huh? K is 2. Thank you. So one way to think about these groups is as automorphisms groups of the point x. So this means something like I have access to automorphism groups of, in principle, all possible orders. Yeah? So these are ways to relate x to itself in a possibly non-trivial way, whereas in a set, in some sense, the only way I have to relate to elements in the set is to ask whether they are equal or not. Yeah? So, but here I have a potentially infinite amount of higher information that allows me that allows me to explain how to relate a point with itself in this groupoid x. So I can also think of sets and groupoids. So every set is a category where the only morphisms are the identity morphisms. They embed into groupoids in the usual sense. So one category is in which every morphism is invertible. And sets can be identified with those infinity groupoids, so that for every point and for every k bigger than 0, pi k of x at x vanishes. And the groupoids are the infinity groupoids with an analogous property, but now I allow for self-identifications, because in a groupoid I maybe have groups of automorphisms at some point, right? But in dimensions 2 and higher, I no longer have such information. So in this way, you can think of infinity groupoids as generalizations both of sets and of ordinary groupoids. So in particular, if you have some groupoid, then you have immediately some infinity groupoid. So one knows many examples. Okay. Yes. Another thing one has is, for example, for two infinity groupoids, well, between two sets, there is a set of functions between them. So between two groupoids, there is an infinity groupoid of functions between them. Groupoid of morphisms. And it satisfies, for example, the Currying adjunction with respect to the Cartesian product. So it behaves as you would expect. And also, for example, it is suitably functorial in X and Y, just as the set of maps in an ordinary category. Now, one of the difficulties of infinity category theory in the presentation I'm using, I did not say this, is there are many ways to present the theory or to materialize the idea I describe intuitively of what an infinity category should be. And using the approach of Joyal and Lurie based on the work of Borman and Vogt on what are called quasi-categories, it is somehow notoriously difficult to write these infinity groupoids in a functorial way. Yeah? So there are very many technicalities in this story that I'm just sweeping under the rug. But as before, we will use this infinity groupoids of morphisms to formulate universal properties. Now there is a distinguished infinity groupoid, which is just a one-point groupoid with no only identity map from itself to itself, which you can think of as the fundamental infinity groupoid of the point. There is some groupoid. And this is the final groupoid. So this plays the role of the singleton in the theory of sets. Yeah? So this is, in some sense, the representative of having only one point with no additional self-identification information in any degree. Yeah? This is the meaning of this object. And with that, for example, we can say, what do we mean for an infinity groupoid to be a singleton in this context? We say in this case that X is contractible. Again, terminology motivated from topology. If the essentially unique map to the final object, so this one-point groupoid, is an isomorphism. Equivalently, what does this mean? Well, X has a single connected component, so that set is a singleton. And it's enough to request that there exists a point in X such that for every positive integer, these homotopy groups vanish. Yeah. So this point X becomes a representative of this point inside capital X. And the path connectivity tells me that I don't need to care about which point I chose. Yeah? Okay, so this, for example, we would like to interpret the saying that X has essentially only one object in a very strong sense. Yeah, that's the way to think about this contractibility statement. We are no longer interested in the question whether something has exactly one point, as in the theory of sets, where, you know, in a bijection, the fiber of an element of the image has a unique pre-image, so that fiber is exactly one element, right? So now we would like to think of something having fibers that are, so pre-images should form a contractible infinity groupoid, so they should contain essentially just one element. Yeah, that's the kind of intuition we want to capture. Okay, so now more terminology. So that was about groupoids. So what can I do if I have an infinity category? Well, for every pair of objects, I have again an infinity groupoid of morphisms between them. Yeah. Again, this is the idea that I want to replace the category of sets by the category of infinity groupoids. Every ordinary category has sets of maps, so every infinity category has infinity groupoids of maps according to this replacement. But now if I have this, I can associate to C a one category called its homotopy category. And this homotopy category has sets of maps given simply by the path-connected components of these corresponding spaces of maps. So that's now this, by construction, is a set. So I can reduce the level of complexity of C by disregarding all this higher information and retaining just the information of an ordinary category. Yeah? So this is very similar as the passage from a digit category to its zero cohomology, for example. Yeah? If you're familiar with that. Okay. And now I can say, for example, what does it mean for an object in C to be a final object? So I can just use my previous intuition from ordinary category theory plus the idea of what does it mean to have exactly a unique, essentially unique point in this context. So an object is final if for every object of C, the corresponding space of maps or infinity groupoid of maps, sorry, from X to this object is contractible. So it is non-empty because it contains essentially one point, but this point is essentially unique. So this should be thought of the existence of exactly one map from X to this point in category theory, right? And by this construction, for example, final objects give rise to final objects in the homotopy category, for example. Yeah? But here we are retaining, much more information. So this, you should compare this to something like some chain complex is acyclic. Yeah, something like this. That's what you would like to compare to. Okay. Okay. So I have something like 9 minutes. Okay. More. Okay, I need to erase. Yes, apparently I do. So I will do first this, then this, then this, and this, and this. Some kind of puzzle. Okay. Nope. No. Go back up. Okay. Somehow I was not convinced by the sound. And my grasp of reality is a little bit weak. Yeah. Okay, let's go one more. Okay. Now, 3. There is also an infinity category at infinity of small infinity categories. Moreover, so this is just similar to the theory. I'm just trying to tell you this is all very similar to the theory of categories. Given two infinity categories, I can form infinity category of functors. And in fact, I just need the first one to be small. Just in the usual story. This also satisfies an appropriate Kerring adjunction with respect to the product of infinity categories and etc. So that's all very nice. In particular, I can look at coherent diagrams. Which is maybe first kind of novelty or difference between the theory of ordinary categories and that of infinity. Well, not first, but a very noticeable difference between the two theories. So functor category from a small category. So for example, if A is commutative triangle, a functor from this to C should be interpreted as something like 3 objects, 3 maps between them, together with some 2-dimensional information that I will denote by alpha, that I want to interpret as something like witnessing the fact that f and g up to homotopy given by alpha composed to H. Yeah? So I don't want to make precise anything of what I mean here. It's just some intuition. But the idea is that, for example, the existence of such a diagram will imply that the classes of f and g compose to the class of H in the homotopy category of C. So this is very similar to what happens in the, say, category of chain complexes up to homotopy. Yeah? So you should model your intuition on that case. But the key point is that I need to specify some 2-dimensional information, even though here I just had this strict equality of compositions. Yeah? So there is some kind of further thing happening there. Now, yes, so there is a way to translate. So you can go from DG and A infinity categories. You can go to infinity categories by some procedure called the A infinity nerve of A due to Lurie in the DG case and to Faonte in the A infinity case. So there is a way to translate from the more algebraic world to the infinity categorical world by some definite formula. Yeah? There is a definite procedure of how to do this in such a way that, for example, the cohomology of chain complexes of maps goes to homotopy of the corresponding infinity groupoids of maps. So there is some compatible way to go from one side to the other. This is some translation procedure, if you want. Yes. So I'm almost out of time. So there is a robust theory of, say, co-limits, adjunctions, and what have you, that one can use. So for example, now one can write a universal property of a push-out, pullback, I will do pullback again, by the existence of a suitably functorial isomorphism of infinity groupoids of this form. Where I'm thinking that I have now this more complicated situation, let me not write this, but using the intuition from this figure, now I want to think of a commutative square more of this additional information where I have this two-dimensional data here in these two triangles, and that square will give me a point in this infinity groupoid. Yeah? And I'm saying that it comes in an essentially unique way from a map from W to the pullback. Yeah? So you can formulate new kind of universal property, replacing bijections of sets by isomorphisms of infinity groupoids. And now, well, to conclude, there is a good theory of localizations. So how to invert maps, arbitrary sets of maps or collections of maps in an infinity category. And for example, using this theory, if you have the category of modules over a ring, then you can form its category of chain complexes. And then there is a localization of it, a very natural one, that we called the derived infinity category of R, which is simply defined as the localization of chain complexes at the class of quasi-isomorphisms, but in this infinity categorical sense. Now, by passing to its homotopy category, we obtain the ordinary derived category. So the one categorical derived category, but crucially, unless the ring is zero, this map is not an equivalence. Yeah? So we get a different invariant of the ring R, this derived infinity category, and so now the punchline of the whole story is that while we know that this is a triangulated category, categorical is not very well behaved. For example, it doesn't have arbitrary kernels or co-kernels, for example, or pullbacks or pushouts. Whereas the derived infinity category, just like this category, has all limits and all co-limits, for example. So this is a much better behaved categorical object. Now the price to pay to work with it is that one must work in a more richer context than the context of ordinary category theory. So just to conclude then, in the next lecture, we will talk about some of the properties that this category has and its relation, so remind you of the standard T structure and other things, and in which way this now becomes universal in this world. Yeah? So we'll explain some universal property and later use this as motivation to go further to the theory of exact infinity categories. Okay, thank you. Sorry for going over time.